Hello everyone. My name is Akshat Soni, and today I am going to present a very interesting topic from our big data subject, parallel big data programming and processing techniques. This topic is extremely important because today almost every company from Google to Amazon to Swiggy means all the company deal with massive data sets. In this presentation, I will explain what big data is, why traditional system fails, and how parallel processing models like Hadoop, Spark, MapReduce, and other helps us handle huge data sets efficiently. Let's begin with the slide 2. Let's start with the basics first. Big data simply means extremely uh, large data sets that are difficult to store, process, or analyze using traditional computers. So big data consists of five V's. First is volume, which means huge amount of data. The second one is velocity, which means data coming at high speed. The speed is measured in it. Then variety means many format like text, images, and videos. Veracity, it indicates towards the quality of trustworthiness of data, and finally the value, which is final useful insights we get from data. So traditional processing fails because one single machine cannot handle so much data. It becomes slow, memory is limited, and real-time processing becomes impossible. This is why we need parallel and distributed systems. So in our third slides, which is need for parallel processing. Now, why parallel processing? In big data, we deal with terabytes and petabytes of information. The data arrives quickly and from multiple sources at the same time, like mobile apps, IoT sensors, websites, and more. So parallel processing helps because it distributes work across many machines. It gives faster executions. It provides scalability. We can easily add more machines. It provides fault tolerance also. If one node fails, other continues. So in some simple words, if we understand it, then the parallel processing is like dividing a huge workload among many people instead of giving everything to the one person. So, what are the concepts of parallel programming? So, parallel programming has two important concepts, which is parallelism versus concurrency. Parallelism means tasks run at the same exact time on different processors. This is what parallelism means. Second one is concurrency, means task appears to run together but actually switch rapidly on a single processor. So there are two types of parallelism. First one is data parallelism. The same operation is applied on different chunks of data. Then task parallelism. Different tasks run in parallel on the same or different data. So this concept helps us break problems into smaller pieces and execute them much faster. Now the parallel big data processing models. So in big data, there are two major processing models: batch processing and stream processing. So batch processing deals with large volumes of historical data at scheduled intervals. Example: generating monthly sales reports. And the extreme stream processing handles data in real time as soon as it arrives. Example: fraud detection on bank transaction or live sensor monitoring. This all comes under stream processing. So both modules are important and used based on the types of applications we use. Now let's see our next slide, which is map reduce model. So now let's discuss on the most influential parallel processing models. The first one is MapReduce. MapReduce was introduced by Google and later implemented in Hadoop. The power of MapReduce lies in its simplicity. It breaks down a large problem into smaller parts that can be executed in parallel. So MapReduce has three key stages: map phase. Map phase, the input data is divided into smaller chunks. Each chunk is processed by a separate mapper. Then mappers generate key value pairs as output. For example, in a word count program, key is equals to word and value is equals to 1. So like this, if we move to the next one, which is shuffle phase, in this stage, all key value pairs from mappers are collected, sorted and grouped by key. So all values associated with the same key are brought together. Then in reduce phase, so reduce process all values. So reducers process all values for each key and generate the final output. For example, summing all the ones to get the total count of a word. So the use cases of this are MapReduce is used for word count, log analysis, data summarizing, and indexing and searching, machine learning basics like clustering. Even though newer systems like Spark are faster, MapReduce built the foundation of modern distributed computing. Let's move towards the next slide now, which is Apache Hadoop. So Apache Hadoop is one of the most popular big data ecosystem in the world. It made big data. It made it possible for companies to store the massive datasets using clusters of ordinary hardware. So Hadoop mainly consists of three components, which is HDFS, Yarn, and Hadoop MapReduce. So HDFS stands for Hadoop Distributed File System. So HDFS stores data across multiple nodes. It automatically replicates data so that even if one machine fails, the data is safe. And the yarn, which is stand for yet another resource generator negotiator, sorry. So yarn manages clusters resources. It decides which machine will run which task and how resources are allocated. So the third one is Hadoop MapReduce. So this is the processing engine of Hadoop. It uses the MapReduce model for distributed computation. So Hadoop become a game changer because it is open source, it is scalable, it can run on cheap hardware, it provides fault tolerance. So many large organizations still use Hadoop as their central data storage layer. So this is all about Apache Hadoop. Now we move towards Apache Spark. Mhm. So, uh, which is Apache Spark, which is currently the most widely used big data processing engine. Spark is known for its speed and in memory processing capabilities. So the key features of Spark is RDDs, which is resilient distributed datasets. These are fault tolerant distributed collection of data. They support parallel operations and can recover automatically if a node fails. The second one is DEG execution. So DEG execution is a Spark built a directed acyclic graph of stages and optimizes the execution plane. This reduces unnecessary shuffling and speeds up processing. In memory processing, which is the third one, unlike Hadoop, which writes intermediate result to disk, Spark keeps data in memory. This makes Spark extremely fast, especially for iterative tasks like machine learning. So why Spark is faster? So Hadoop is disk based, Spark is memory based. Spark supports real time processing, Hadoop is mostly batch time. Spark has a simple API in Python, Scala, Java, and R. And Spark is ideal for ML also, machine learning, because streaming and graph processing are there in Spark. Now let's move toward next slide, which is other big data frameworks. So, there are other frameworks that specialize in real time and streaming workloads. Apache Flink, so known for true real time stream processing with very low latency. Then, second one is Apache Storm, an older system but very reliable for unbounded streaming data. You can read out from these three types of Apaches. So the third one is Apache Kafka, a distributed streaming platform used for data pipelines, event streaming, and real-time analytics too. So most modern companies combine these tools. For example, Kafka for ingestions, Spark for processing, and like Hadoop for storage. Like this, modern companies combine these tools and use them. So let's move to the conclusion part. Hmm. To conclude, parallel big data processing has become a backbone of modern data driven industries. So, the key takeaways which we have taken from this PPT is big data cannot be handled by traditional systems. Parallel processing divides work across multiple machines. Hadoop, Spark, MapReduce, and streaming frameworks are essential. So, these technologies enable real time insights, faster processings, and scalable solutions. Now, the real world application includes social media and our e-commerce recommendation, social media analytics, fraud detections, healthcare predictions, IoT monitoring, scientific simulations. All this comes under our real world applications for this topic. So now, thank you for listening and understanding. I hope this presentation helped you understand how parallel techniques make big data processing efficient and scalable.